Okay, let's unpack this. You've got the power of what, 1,000 1980s supercomputers sitting right there in your pocket.
It's pretty incredible when you put it like that.
So our mission today is to give you a shortcut. We want to map the major technological leaps that took us from, say, counting beads to generative AI.
But focusing only on the real aha moment.
Exactly, the conceptual breakthroughs that actually made the device in your hand possible.
And what's fascinating is how long that conceptual groundwork really took. The need to calculate is ancient.
You're talking about things like the abacus.
The abacus, yeah. And then much later, you get mechanical devices like Pascal's calculator in 1642, which could automatically add and subtract.
But the real foundational insight for modern computers wasn't just about math, was it? It was a conceptual leap.
It was, and that brings us to Charles Babbage.
The father of the modern computer. But his analytical engine was purely mechanical. I mean, how much of that blueprint was even useful once electricity took over?
Well, that's the core insight, isn't it? Babbage separated the instructions, the program, from the data it was processing.
Using punch cards.
Using punch cards.
Yeah.
That architectural separation is, it's the definition of modern software. It doesn't matter if you're using gears or silicon.
And you can't talk about Babbage without mentioning Ada Lovelace.
You absolutely can't. She wrote the first program for that machine, and she realized its potential to go way beyond just crunching numbers. She was the first programmer.
So, okay, let's fast forward. We get to the 1940s, and suddenly Babbage's concept is realized electronically with the first generation. But the scale, it's just staggering.
Oh, it was an engineering nightmare. Machines like ENIAC and UNIVAC literally filled entire rooms.
They were built on vacuum tubes.
Thousands of them. Fragile glass vacuum tubes. And you have to imagine the impracticality of that. The excessive heat, things were always breaking, the amount of electricity they used.
All just to run calculations that were, by today's standards, incredibly slow. It's just amazing how quickly we went from that fragile glass tube to a chip.
Yeah.
So the second generation, starting around 1956, that's the transistor.
The transistor. That was the essential miniaturization step. Machines suddenly got smaller, they got faster, and they were so much more reliable and used way less power.
And that just accelerated into the third generation N64.
Right, with the integrated circuit or the IC, instead of single components, we could suddenly print multiple transistors onto one tiny silicon chip.
And that's when we start to see things we recognize, like keyboards and monitors.
Yes, user interaction starts to evolve right around then.
Which sets the stage perfectly for the fourth generation, the one that defines, well, everything we use today. The microprocessor.
The Intel 4004, 1971.
The entire central processing unit on a single chip. And this breakthrough isn't just about speed, is it? It's about access. It's the democratization of technology.
Precisely. That explosive increase in density and the costs coming way down, that's what put the personal computer.
And that leads directly to your smartphone.
It does. We went from room-sized machines using physical punch cards for storage to a smartwatch that can perform billions of calculations per second.
And now we're pivoting into what people call the fifth generation, the age of AI.
Mm-hmm.
It's no longer just about calculating faster. It's about a machine that can actually learn.
That's the fascinating functional shift. You now rely on systems using machine learning, natural language processing.
Like ChatGPT.
Exactly like that. Systems that can understand context, that can drive a car, that can help diagnose diseases. The computer has evolved from just a tool to an analytical partner.
So we've gone from mechanical gears to intelligent systems in, what, a few decades? The speed of this evolution is just accelerating so dramatically.
We've really seen computation become ubiquitous. It's moved from that room-sized fragility to just pocket-sized power.
So here's a final thought for you to consider. If the fundamental leap from Gen 1 to Gen 4 was all about massive miniaturization and speed, what new fundamental principle, beyond our current focus on deep learning AI, is going to define the next generation of computing? What will that next essential technological shortcut even look like?